to lecture here. I think we just had maybe a slide or two left about buffers, so we'll just kind of just review about talking about buffers here, and then we're going to go into 17. So last time we sort of finished up talking about, like I said, buffers, and a reminder that basically a buffer is a solution that's able to resist big changes in pH. So again, for example, if you had a buffer that was at a pH of 6, it wouldn't go all the way up to say a pH of 12. If you added some base to it, it wouldn't go all the way down to say a pH of 1 if you added some acid to it. But it's able really to resist changes in pH um, when you add additional acid or base to it. And really, the reason it's able to do that, as we sort of talked about last time, is it's really made up of a combination of one of two sort of combinations, either a weak acid and its conjugate base, or again, sometimes referred to the salt of its conjugate base, or it's a weak base and the salt of its conjugate acid. And what that really means is because these are weak acids and weak bases, they don't 100% break apart or dissociate in solution. They actually set up an equilibrium. And because they set up an equilibrium, what that means is when you have a buffer solution, it actually has sort of a acid part and a base part basically floating around in that solution to begin with. And that's crucial for having an actual buffer, and actually a buffer that will sort of work correctly is having both of those things in there to begin with. So for example, if we were talking about, like I think we did last time, HF and say sodium fluoride. HF is a weak acid. Sodium fluoride is really a source of F minus, which is its conjugate base. And if we had, say, a buffer that was made up of that, what that would mean is when we would put it into solution, we would have HF guys floating around. We would also have a lot of F minuses floating around in that solution just to start with. And that's because, again, HF is a weak acid. It's a weak electrolyte, which means when it goes for a swim, it's going to break apart into ions, which is able to produce some F minus and also allow some HF to also be in that solution at the same time. And that's again critical because when we add additional acid or base to a buffer, so if we added, say, some hydrochloric acid to a buffer, what's going to happen is when that hydrochloric acid goes in, or even if we added it into here, it's going to break apart into H plus and Cl minus. Cl minus is not important. It's not going to really do anything. But what's going to happen is when that H plus goes in there for sort of a swim, it's going to actually come together with the F minus that's in there originally. And what's it going to do is basically produce some more HF. And when we would add, say, the hydrochloric acid, the reaction that we would see would be something like this. And what we produced is more HF that was there originally, which is not going to mess up the pH at all. But more importantly, what happens is, as we talked about at the end last time, is we really don't produce any more free H plus. And it's really that production of free H plus that really makes the pH kind of go crazy and drop or go higher or lower a lot, is that production of that free H plus. So because we didn't produce any more free H plus coming in from the HCl, for example, that we added in there, the H plus concentration remains relatively constant and the pH also will remain relatively constant. And again, that's because the pH is equal to minus the log of the H plus concentration. And the same thing would happen if we went and added, say we added to this buffer. Again, we have HF floating around, F minus floating around. If we added some, say, sodium hydroxide to it, again, when we would dump something like sodium hydroxide in here, again, sodium hydroxide is a strong base. It will break apart into Na plus and OH minus. The sodium is actually a neutral salt. you take 200 or 1B, you'll learn about that. Not important. But what we actually did here is produce some OH minus. But what happens in this case is the HF that's there and the OH minus will react and basically form water. So the H from the HF and the OH minus comes together to form water. And ultimately what we get is that this type of reaction here. And what we make is water, which is not going to affect the pH. We also make sodium fluoride, which was part of the buffer to begin with, not going to affect the pH. But most importantly, when we add a base, is we don't actually make any free OH minus. And that's really important because, as we talked about earlier, H plus and OH minus, they are tied to each other. So as one goes up, the other goes down, and vice versa. So if we're able to basically maintain the amount of OH minus in that solution, we're also able to maintain the amount of H plus in that solution. And we're also able to maintain the pH of that solution as well, because we don't get a big change in the amount of H plus. So ultimately, that's sort of how a buffer works and why it has to be made up of something that's a weak acid and its conjugate base, or a weak base and its conjugate acid. Because that weak acid and that weak base, depending on which sort of you choose for your buffer, it's able to set up that equilibrium where it allows both of those things to stay in the solution, allows really an acid part to stay in the solution and a base part to stay in the solution. And that's what allows a buffer really to prevent the formation of free H plus or OH minus. And really, ultimately, what all that does is it maintains that H plus concentration in that solution where it started. And because that really doesn't move all that much, the pH of that solution is able to basically maintain. The other important thing that we talked about last time was the idea that buffers are not necessarily a neutral solution. You can make a buffer at a pH of 7. You could also make a buffer at any pH you want, anywhere from an acidic buffer to a basic buffer to a neutral buffer. The key is wherever you start with your buffer, say you made a buffer at a pH of 9.25, if you added acid or base to that buffer at 9.25, it should pretty much maintain that pH of 9.25. Will it go up or down when you add acid or base? In reality, the answer is yes, it will. So if you had like a pH meter, which you can use to measure pH, and you put it into a buffer solution and you added some acid, what you would see is it would go down, but it wouldn't go drastically down. So maybe it started at 9.25, maybe it goes down to 9.19, 9.15, something like that. It wouldn't go from 9.25 if you added acid all the way down again to a pH of 2. So you want to see a dramatic change in the pH. You will see a slight change in the pH. Again, if you added acid, it should go down a little bit. If you added base, it should go up a little bit. Any questions on that there? And ultimately, again, you could sort of think about a buffer as working pretty well in this sort of context. As I mentioned before, there's again an acid part of the buffer, there's a base part of the buffer. And basically, as we talked about, when we add acid to a buffer, it will react with the base part of it. And we will actually make more of the acid part of the buffer. We'll use up some of the base part of the buffer. And same thing happens kind of going the other way. If we added base to it, the base that we add would react with the acid part of the buffer, and we would actually make the base part. So it sort of regenerates itself, part of it, as you're doing these sort of additions of acid and bases to it, but it is using up part of the other of the buffer as well. And you can see if you didn't follow instructions and you just decided, hey, I'll just keep adding acid, at some point you will keep eating up the base part of the buffer to a point where it won't be able to maintain the pH anymore, and you will see a big jump in the pH. So there's something known as sort of buffer capacity, and when you make a buffer, you want to make it appropriate for the pH that you want and also the concentration that you want. So if you grabbed off the shelf really strong acid and you dumped it into a buffer, what you're adding in terms of acid may be way too much for your buffer to handle, and it may, for example, just burn up all the base part of it, and you would definitely start to see it. So that's why a buffer can really maintain a pH over a long period of time, because you know, as you sort of use part of it, you make the other part. So you could kind of keep those ratios in an okay situation that's able to really handle a lot of addition of acid or base. Again, as long as everything's sort of made correctly. Any questions on that there? So, which of the following would be an appropriate salt to make this buffer? So we have carbonic acid, which is a weak acid. So we would want its conjugate base. So remember that the difference between this should only be 1H plus, right? So if this is an acid, it's going to donate its H plus, and we would end up with something that looks like this as really its conjugate base. And what makes it the salt of its conjugate base is we put a positive guy on there to balance out the charge. So if we put something like sodium here to balance it out to make it a salt's just an ionic compound. We should end up with something like NaHCO3 would be the appropriate salt to make this buffer with, which looks like it is D here would be the right answer. And if we were to make this buffer, there's a couple ways you could do it, but the most common way is you would measure out the appropriate amount of this. You would also measure out the appropriate amount of that, dissolve it all in some water, and make a buffer solution. And again, if we did this in that buffer solution, you would have some HCO3 minus floating around. You would have some H2CO3 floating around. This would be your acid part. This would be your base part of your buffer. And again, they both would be in that beaker to begin with. Any questions on that? Let's see here. Solution containing NH4Cl is buffered with NH3. Which of the following reactions is likely to take place if a strong base such as sodium hydroxide is added? So in this case, what we have going on is we have NH3. NH3 is a weak base. NH4Cl is really a source of NH4 plus and Cl minus. This is actually a salt here. And the relationship that is the buffer is the NH3 and the NH4 plus. So that's the weak base. This would be its conjugate acid. And really those two things, the chloride has no effect really on anything. It's just floating around to balance out the charge. Those two things floating around in this solution is what makes up the buffer. Again, this is the base part of the buffer. This would be the acid part of the buffer. So if we dump in some sodium hydroxide, which is really a source of sodium ions and hydroxide ions, in terms of pH, the sodium has no effect. So we're really talking about when we dump this in here, the hydroxide, which is a base, right? So if you think about the reactions, it's an acid-base reaction. So we would expect the acid part of the buffer to react with the base that we're adding. And we should get some type of reaction that is NH4 plus some sodium hydroxide. And again, this is the acid part, which means it's going to donate its H plus over, and we would get some water that is formed and NH3. And obviously we have some sodium happening there as well. So it looks like perhaps it is B would be the right answer here. But again, what happens on the product side, no OH minus free in that sense. It gets pretty much tied up here where it makes water. And again, because the OH minus did not increase, the H plus concentration would not increase. And again, we would expect the pH to be maintained here. Any questions on that? This, by the way, would be a basic buffer, just so you know. If you made this buffer, you're probably looking at a starting pH of about 9.25 in that ballpark. So what would happen if we added the sodium hydroxide is, again, the pH would remain around that 9.25 level. It most likely will go up a little bit, but it wouldn't jump tremendously. You won't see a big jump in the pH. Any questions on that? All right, that is it. Actually, those last couple of slides from 16. Any questions on that? Just want to kind of go over buffers a little bit more than what we kind of finished up on last time. Any questions on chapter 16? Okay. That is as well the last chapter that's on our exam that's on Monday. So it is 15 and 16 that should be on that exam. All right, we're off to then chapter 17, which is the last one of the season here. So this is equilibrium. Um, and we're going to talk about equilibrium. We'll get into sort of what's happening, what's referred to as Le Chatelier's principle. And you'll really, if you continue on with chemistry and you go take Chem 1B, this is pretty much all you talk about in Chem 1B is equilibrium. Every type of equilibrium you could ever dream of, you cover in that class. So you probably won't see too much of it in 1A, but again, you'll see a lot of it again in 1B if you go that far there. So let's talk a little bit about equilibrium and sort of the idea of what happens when a reaction takes place. So really the idea of what is sometimes referred to as collision theory is the idea that a reaction really takes place as a result of really two things coming together. But does a collision necessarily mean that you will make products? And the answer is no. So not all collisions necessarily will result in sort of products being made. And what we're talking about here is reactants basically coming together and colliding and products being formed. As a reaction takes place and as a reaction goes on, what essentially has to happen is basically all of our reactants pretty much has to break all their bonds, right? And basically they need to reassemble on the other side as our product. So they need to make all these new bonds here. And as a reaction sort of takes place, there's sort of a transition that occurs in this process. As they collide and a reaction takes place, you're starting to get everybody breaking bonds, and they slowly start to form these new bonds and new guys on the other side until they kind of come down. There's actually, as we will see probably in this chapter as well, sort of an energy diagram. So as that process is happening, you have your reactants, they're starting to break bonds, and they're making partially new bonds. And you get something like way at the top that's very high in energy, if this is energy over here. And eventually they will then make their new products on this other side coming down this hill. So there's sort of a hill of energy that occurs as that process is happening. Does things need to come together and collide? They do. But they do need to collide in sort of the right area. So they do need to hit each other in sort of the active side, if you will, in that right sort of location in order for a reaction to actually take place. In addition, they also need to really come together with the right amount of energy to allow products to be made. As we'll talk about probably a little later in this chapter as well, that energy is sort of this hill, this activation energy that everybody has to climb basically to get to the other side. So reactant concentrations, usually higher concentrations, do lead to more collisions. More collisions mean that we typically will form more products. So if you think about if you have a really high concentration, and when we talk about concentration, something like molarity, which is really moles of solute per liter of solution. And really what's reacting when we have something like a solution is actually the moles part. So there's only a certain number of moles of your solute in here. And that's really what is available to sort of react with each other. And if you have a larger concentration, what that means is you have more moles of your guys kind of floating around in the solution. And the more moles that you have floating around the solution, there's probably a greater chance that they will come together and start reacting rather than a very low concentration, which means you don't have a lot of guys floating around in that solution. And that means it takes longer for them to sort of find each other and collide and sort of start the reaction off. Also, temperatures usually will affect it. Reactions typically go faster at higher temperatures. So when you think about higher temperatures as well, higher temperatures means usually more energy. More energy means that typically things are moving around a lot faster. And that means that they're more likely to come in contact with each other a lot quicker as well. And in addition, at higher temperatures, they also will probably have the right amount of energy that when they do come together and sort of collide, that products would be formed. So those two things are really important in terms of rates of reaction. So when we talk about a rate, which is also something that you talk about, I think, in Chem 1B, which is kinetics, it's basically how fast or slow a reaction typically takes place. So typically, if we increase the temperature, in fact, if you sort of increase the temperature usually of a normal reaction by about 10 degrees Celsius or something like that, the rate usually will double. So the reaction will go twice as fast as a result of that. And again, just because of the higher temperature, everybody has more energy, everybody's moving around a lot faster, takes a lot less time for everybody to come in contact with each other and really kick off a reaction to happen. The opposite would be true as well. Again, if you lowered the temperature, so if you kind of put everything on ice, so if you did this reaction like at room temperature, or you did this reaction after you put everything in, like, say, hot water, and let it sit there for a while, or you took everything and did everything sort of in an ice bath, you would probably see that the ice bath in a lot of reactions would typically happen a lot slower. Again, everybody has a lot less energy, they're moving around a lot slower, and even if they do come in contact with each other, they might not actually have that sufficient amount of energy to make that reaction take place. And what is that sort of minimum amount of energy that's needed for a reaction to take place? That is what is known as the activation energy. And the activation energy is the energy that's required really for a reaction to take place. It is really the hill that a reactant has to climb to get to the other side. And what we're looking at here is sort of what is referred to as an energy diagram. And there's kind of two types of energy diagrams you typically will see. I'm going to badly draw it here, but I'll give it a try here. We'll go this way. And if this is the reactants here, this is the products. Again, this is energy over here. This is the reaction diagram for a exothermic reaction. And exothermic means, as we've talked about, that heat and energy is released. And that is very easily recognized by the location of the reactants and the products. Here we see that the reactants are higher in energy than the products. And that means in order for our reactants to get down to our products, energy has to be given off, right? And that's an exothermic diagram. So if you see a diagram like that where your reactants are higher in energy than your products, that is definitely going to be a exothermic one. Endothermic reaction, which is sort of our opposite, looks different. It's kind of similar, but a little bit different. Looks something like this. And here, this is our reactants, this is our products, and this is our energy. And again, here what we see is this is going to be an endothermic reaction, which means heat and energy is absorbed. And in this sort of reaction, what we see when we look at the diagram is the reactants are actually lower in energy than the products. And that means energy kind of has to be put in to get our reactants up there to our products. So what's happening, as you can kind of see in this diagram to our right here, is these are our reactants. And as it's making its way up the hill, we're starting to get our bonds to break, and we're starting to make some of our new bonds. And this hill that we see is what is known as the activation energy. And that's the minimum amount of energy, as it says, for this reaction to occur. It is basically that hill that the reactants have to climb to get to the other side. Now, if we look at our exothermic reaction, this right here is our activation energy. And if we look for our endothermic reaction, this right here would be our activation energy. And we could see that in a exothermic reaction, the hill is usually a lot smaller than an endothermic reaction. And that sort of makes sense. In an endothermic reaction, energy has to be put in to help everybody up and over the hill to get to the other side. Exothermic, you sort of have excess energy, so it's not as big of a hill to climb to get to the other side. When we do reach the very top, as you can see here, this is what is sometimes referred to as the transition state. And what we get at the very, very top, and these guys would be the transition states there, we get what is sometimes referred to as the transition state complex. or the activated complex is sometimes called. And what that is a substance like we see here in this picture where we have something that has partially broken bonds and also has some partially made bonds. So it's sort of a transitional kind of species where it's starting to break all those bonds of the reactants, but at the same time, it's really making all the new bonds between our products. And you get something that's very, very high in energy. And one thing that we should know is things that are very high in energy are not very stable, right? Things like to be in lowest state of energy. And when we get something like a transition state complex down the top there that has those partially made bonds, partially broken bonds, we get something that's very, very unstable. And typically what happens is it very quickly will then kind of drop down to the other side. You know, it's very unstable. It doesn't want to really be there in that very high state of energy. It will really drop down to the products really quick. And that's why a lot of times these sort of species on the top of the hill there, those transition state complexes, they're very hard to isolate because they really don't hang around a very long time. They very quickly kind of drop down to the hill. Now, this activation energy obviously plays a big role in the rate of a reaction, how fast or slow it occurs. If you have a very big activation energy, that means you have a very big hill to climb to get to the other side. You would expect it to be a slower reaction than something that has a very small activation energy, is be able to get to the other side a lot quicker. Any questions on any of that there? Okay. Another way that we can sort of speed up a reaction is to add a catalyst. And a catalyst is a substance that will speed up a chemical reaction. It actually can slow down a chemical reaction, but most people, when they talk about a catalyst, talk about it in the sense of it actually speeding up a chemical reaction. A catalyst is not a reactant, it's not a product, and it actually does not get used up in the reaction. So the catalyst is actually still there at the end of the reaction. Really, the sole purpose of a catalyst is to facilitate that reaction occurring a lot faster. That can mean simply it's a solid catalyst that, you know, attracts everybody to sort of a central location where they then can come in contact with each other a lot quicker than if they just kind of had to float around and find each other. And a lot of times that's how catalysts sort of work. Sometimes the environment also helps out. So sometimes we use things like acid as catalyst, and it creates sort of an environment where there's a lot of extra, say, H plus floating around in that solution, or maybe sometimes OH minus is needed. So there's a lot more OH minus, which just facilitates these reactions to occur a lot. A lot of times in chemical equations, we see catalysts written above the arrow. So sometimes you'll see something like platinum there. Maybe you'll see H plus, which means it's like an acid catalyst. So a lot of times catalysts are written sort of above the arrow in a chemical equation or reaction. And again, they're not a they're not a reactant or a product, just really there to facilitate that reaction happening a lot quicker. So sort of the mountain sort of example, you know, if you had to kind of go up and over the mountain to get to the other side, it's going to obviously take you a lot longer than, say, if you're like the coyote, right? Open up the door and the mountain just went right through to the other side. And like cartoons, right? You find an alternative path to get to the other side and you're going to get there a lot quicker. So ultimately, what a catalyst actually does and how it's able to sort of speed up a chemical reaction is by finding that alternative pathway, it actually is able to lower the activation energy. So that's ultimately how a catalyst actually does speed up the reaction is it finds that alternative pathway. What it means is you don't have to go all the way up the giant hill. You have just a smaller hill to climb to get to the other side, and it allows that reaction to take place a lot quicker. any questions on that as well. All right, so let's talk about equilibrium. And first off, let's talk about equilibrium and really what it means. And first off, in terms of chemistry and chemical reactions, equilibrium reactions really involve a certain type of reaction. And these are types of reactions which have these arrows that head in both directions. So they usually are involved in what are sometimes referred to as reversible reactions. And in a reversible reaction, you could definitely see it by those arrows that are going in both directions. And in a reversible reaction, what that means is we have reactants going to products, which is sometimes referred to as the forward direction. And we also have some products that then can come back together and make the reactants, which is referred to as the reverse direction. And what does it mean when we come to equilibrium? Well, sometimes people mistakenly think that what it means when we reach chemical equilibrium is we have the same amount on both sides. So we have the same amount of reactants and the same amount of products. And that's really not what chemical equilibrium means. Actually, what chemical equilibrium means is at some point, the rate of the forward reaction will actually equal the rate of the reverse reaction. So what that means is as quickly as it goes to products, those products will just as quickly go back the other way. And what that really means is you don't necessarily get the exact same amount on both sides, but you get everybody locking into place when that occurs. So what I mean is if you have something like this reaction here, A plus B goes to C plus D, and if we say started with 4 and 6 and 3 and 2 of these guys, and then we reach equilibrium. At that point, maybe this guy locks into 2, this one locks into 3, 1 and 3 over here. Once it reaches equilibrium, if this say was the molarity of each of those things, they would basically maintain that molarity at that point. It doesn't mean that we have exactly the same amount on both sides. It just means that once they sort of lock into equilibrium, because it's going back and forth at the same rate, everybody sort of locks into where they are in terms of their concentration. And they pretty much won't change because, if you lose a little bit to the right, some of it comes back to the left, and everything basically maintains where they're at that point. So one very big misconception sometimes students have about equilibrium is that once we reach equilibrium, hey, I got 5 on this side, I should have 5 on this side. It's at equilibrium. And again, that's not really what it means. It's really talking more about how fast it's going in one direction is just as fast as it's going in the opposite direction. And because of that, everybody can sort of maintain where they're at and they sort of lock into place. This happens, for example, if you put a solution into a container with a lid on it. At some point, what's going to happen as soon as you put that solution in that container, you're going to get a big rate of evaporation, and evaporation happens at the liquid surface all the time. So you can get a lot of these guys coming out of solution and starting to evaporate into gas. Because there's a lid on it, it's got nowhere to go. And basically, a lot of those guys are then going to start to drop back into the liquid phase and go through condensation. And at some point, these rates will equal each other. The rate at which those guys are jumping out of solution is the same rate at which they are basically coming back into solution. And you will see that that liquid in that container will reach equilibrium. And in reality, what you will really see, which you can't really see here, is usually you'll see a slight decrease in the amount of volume that was there from originally. And that's when once it reaches equilibrium, the actual liquid level will come down a little bit. So when we talk about chemical equilibrium, it's a dynamic state where concentration of reactants and products basically remain constant. But sometimes if we were to look at, for example, if we were to look at a beaker that was going to equilibrium and maybe it started out kind of reddish, and then you would look at the beaker later, maybe it looks a little bit colorless there at that point, and you could be looking at the colorless beaker and go, oh, the reaction's over. There's nothing really happening. And you can actually be looking at it and go, I don't really see very much happening. And on the sort of the big level, the macroscopic level, there's really not much that's happening or changing. But if you were to sort of super zoom down in to the molecular level, you would see a lot of activity happening, because when this thing reaches equilibrium, even though visually it looks like not much is happening, if you zoomed in, you would see a lot of guys going to the product side. You see some of those guys going back the other way. So there's a lot of activity going back and forth on the molecular level that basically keeps it, sort of looking like nothing much is changing. And not a lot is changing, because at that point, everybody is sort of locked into place. Any questions on equilibrium there? And again, that's what we could kind of see here. You can also see a little decrease in that liquid volume at the point when it reaches equilibrium. Again, there's going to be a slight adjustment as things keep going back and forth out of the solution. Again, here's another sort of picture of what we're talking about. And again, as a reaction of water and CO to form CO2 and H2, as time passes, again, we see a lot of activity. But at some point, once it reaches that equilibrium, everybody's going to be able to basically maintain where they're at that point. Again, because it's going back and forth at a pretty good rate at that point. And they're able to maintain that. Can you do something to screw that up? You can. We're going to talk about that a little bit later on in this chapter. You could get a system to reach equilibrium, and then you can actually do something to it that will mess it up. But the nice thing about it is the system itself will want to once again get back to sort of equilibrium. So that's what's known as Le Chatelier's principle that we'll talk about a little bit later on in this chapter. But um, you get a system to equilibrium, you could actually do something, screw it up, and it will want to come back to equilibrium afterwards. So changes with time and rates of the forward and reverse reaction. So when we have a reaction, really, something like what we see here, at the very beginning of the reaction, we pretty much have all reactants, which is kind of this blue line. We have all these reactants. And we pretty much have none of our products. And remember, in order for this reaction to happen, we got to use up some of our reactants to make our products. So when we do that, we do expect to see what we see here. The amount of reactant starts to decrease because we need to use some of those to make our products. And at the same time, we see the amount of products start to rise. And at some point, they're all going to plateau out here in this line here. And this is the point where chemical equilibrium has been reached. Basically, the rate of the forward reaction will equal the rate of the reverse reaction. And the way you can recognize that is, before I just kind of scribbled all over it, this is basically the plateau line. It's flattened out, which implies that neither concentration at that point is changing. So we don't have, this line here continuing to come down. We don't have the other line kind of continuing to skyward up, or this guy coming down. They both basically at that point level off, and what that means is they both basically are maintaining their concentration for the rest of the run here. And again, at that point where they do level off and plateau, that is where we have reached chemical equilibrium at that particular point. Any questions on that? So graphically, if you were asked, what point, equilibrium is reached, you always want to kind of look for that plateau line that occurs, that kind of straight line that occurs. And again, what that's implying in a graph like this, that everybody's basically maintaining their concentrations and equilibrium has been reached. So if we look at this sort of reaction here, H2O plus CO, and it goes to H2 and CO2, this again is a reversible reaction. We could recognize it by the arrows heading in both directions. If we added more H2O to the flask, how does the concentrations of each of the chemicals compared to their original concentrations? So that's a good question. So why don't you take a second and think about what would happen if we have the system and we add some more H2O to it? What happens to everybody's concentration? So H2O. So first off, we want to think about where H2O is in this reaction, and it is actually over here on the reactant side. So if we increase this guy and added more, basically, what that should happen, or what should actually happen, is there's going to make a lot more H2O available. And because there's a lot more H2O available, that means that the CO should be able to find it pretty quickly. And really what this should do is it should kind of kick off the forward reaction. So it should kick off this reaction heading towards the product side. And what that would mean is, because we sort of kicked it off heading towards our product side, we would expect on our product side, the amount of H2 should start to increase compared to where it started. We would also expect the amount of CO2 to increase from where it started, because we are heading to the product side. How about the amount of CO? The amount of CO should actually start to go down from where it started. Remember, to make our products, we need the H2O and the CO basically to come together to make the products. Now, what about our H2O? Well, our H2O is kind of an unusual sort of case. You're probably going to see two things happen with the H2O. The first thing you're going to see happen with the H2O is it is definitely going to go up. And it really only goes up because you artificially added it. You decided to pick it up off the shelf and dump it in there. But once it goes up, you then should start to see it come back down, because as soon as it goes up, it's going to start reacting with the CO, and you're going to need to use some of it to make products. So what you'll actually see with the H2O is H2O will go up. It probably will come back down. And depending on how much H2O you added, it may actually end up higher than it started with, only because you artificially added some more H2O. Yeah, so in terms of the CO, I'm not sure your question. If you're asking just in context to this, the CO in either case would probably continue to go down. Even if it was the limiting reactant, it actually is becoming like the limiting reactant in this case. Obviously, if we added a lot more H2O, we kind of have excess H2O, which means that it's definitely going to go and react with the CO, and we would expect, obviously, it to continue to go down. It may even go down a lot, almost to nothing. But remember, it is a reversible reaction. So even if it goes down almost to nothing, you are going to at some point get some of these guys coming back this way to bring back up that concentration a little bit. So in reality, it probably won't bottom out or sort of zero out in a lot of cases, because you will have that reverse reaction kind of building it back up in that sense. But in either situation, if the result of whatever you did to this reaction makes the reaction head towards the product side, you would expect both reactants to go down. The only difference is in this case with the H2O is because you artificially added it, it's definitely going to go up first, but then it should come back down as it's starting to react. Other questions on that? Okay. So let's take a look at this. Think what will happen if we added more H2 to the same guy. What happens to everybody's concentration in this particular case? Except in this case, we're adding H2, which is over here on our product side. So definitely we're going to see an increase in the H2. And because there's an increase in the H2, that's going to make it more available for the CO2 to react. And what this is going to actually do is kick off the reverse reaction to occur. So you're going to kick this reaction off, and it's actually going to be heading from the product side to the reactant side in this particular case. And because of that, since we're heading towards the reactant side, we would expect the amount of H2O to actually increase in this case. We would also expect the amount of CO to increase as well. Same sort of thing as what we were talking about before. In order to make both of those things sort of increase, we need this reaction to occur between these two guys. And that's going to make the CO2 go down because of that. And just like what we saw with the water in the first example, what we'll probably see with the H2 is here, it will go up because, again, you artificially added it. But once it starts reacting with the CO2 in this case, you should start to see it come back down. And again, a lot of cases, it sometimes will end up a little bit higher than it started with, just because you artificially added it. So basically what we're seeing here is, by making a reactant sort of available, we're going to allow that reaction basically to sort of take place. So when we do that, we're basically screwing up the equilibrium here. So if this thing was at equilibrium by adding more H2, we're definitely screwing up the equilibrium because we're forcing this reaction basically to head to the left for a period of time. At some point, everything will sort of settle back down. And again, the rate of the forward reaction will again equal the rate of the reverse reaction. And it will once again sort of achieve equilibrium at that point. Any questions on either of those? So there is a relationship that we have for equilibrium sort of reactions, and this is what is known as K, and it is a capital K, lowercase k, which is a rate constant. So actually, capitalizing the K is really important here. It is capital K here, which is our equilibrium constant. And it is a constant, which means for a particular reaction at a particular temperature, you will get the same relationship. So it's sort of a relationship of basically our products over our reactants. So if we have this generic equation of A plus B goes to C plus D, we could write the equilibrium expression as the concentration of C, and we take our coefficients, they become our exponents. To the C, our concentration of D to the D, divided by the concentration of A to the A. Again, coefficients become our exponents, and B to the B here. So this sort of ratio gives us a constant value, and it is a constant value for a reaction. Again, very specifically, the couple of things about the K that you see. If you ever see a K value given to you, it is specific for the reaction like it's written. What I mean by that is whatever's on the reactant side is on the reactant side, whatever's on the product side is on the product side, and it's also for a specific temperature. Capital K or the equilibrium constant, the only thing that ever affects the actual value of it is temperature. So if you change the temperature, the value of K will change for that reaction. And what I mean by that is you can have a reaction, say like this guy here at 25 degrees Celsius, it will have a certain K value. If you change it to say 80 degrees Celsius, it will have a different K value. The difference between 25 degrees Celsius's K value and 80 degrees Celsius's K value will be two different numbers. It also means, and this is also sometimes very difficult for people to understand with equilibrium, is you could actually start with different amounts. So what I mean is, for example, you did one reaction where maybe you started with 5 molar A and 6 molar B. And when it comes to equilibrium, if it's at 25 degrees, it will come to equilibrium with, like, say, a K value of 5. I'm just making these numbers up. And say you did the exact same reaction at 25 degrees and you started with 10 molar A and 7 molar B. It will also come to the exact same equilibrium value at 25 degrees. We'll just say 5 again. If you took that same reaction and you changed it to 80 degrees Celsius, it will come to equilibrium. And even if you started with the same amount, it will come to equilibrium with, say, a different value, say an equilibrium constant of 12 or something like that. And temperature is the only thing that will affect the actual value of it. You could start with varying amounts of your reactants and your products, and it will always come to this ratio of products to reactants. There will always be the same number. And again, sometimes people go, wait, I started with like 20 milliliters of this guy the first time, I did 60 this time, the second time, how come I keep getting the same K value? And that's just how that sort of ratio always works out. It will always come to the same ratio of products to reactants, even though they may not be the same numbers, but that ratio that you get of products to reactants will always be the same sort of ratio as long as you don't change the temperature. And it will always end up the same way. So what does the K value tell us? And by the way, this is what Chem 1B is all about, capital K there. It's all you solve for. Every type of K you could ever imagine, you will see in Chem 1B. But it does actually tell us some important information. If we have a large value of K, for example, what that means is when we reach equilibrium, because this is really products divided by reactants, if we have a large value of K, that means we should mainly have products at equilibrium. So if you just think about mathematically, large number divided by small number gives you a large number. If you have a small value of K, it tells us that we mainly have reactants at equilibrium. So when we reach equilibrium, we have mainly reactants at equilibrium. And again, opposite way, with small number of products divided by large number of reactants gives us a small number as well. So K tells us if we have a large value that when we reach equilibrium, we should expect to mainly see products have been formed. If we have a small value of K, when we reach equilibrium, we should expect mainly reactants to be there. What is a large value or a small value? It is that large number of 1. So anything above 1 is considered large. Anything less than 1 is considered small. So less than 1 is small. Anything above 1 in terms of K is considered large, and that big number 1. And really, because 1 is, in order to get 1, you would need to have the exact same amount of products and reactants. So that's why 1 is sort of our defining sort of large or small value. The other nice thing about K is if you calculate K, it is actually just a number. So no units associated with K usually. So usually no units with K. It's usually just a number. And again, that number is very important in a lot of calculations. And as I mentioned before, in 1B, it's very important to understand that relationship. It allows you to do the right type of calculations. So if we have this this reaction here, we want to write the K expression. We would take the concentration of NH3 and we would square it because of the 2 that's there. We would divide it by the concentration of N2, which the coefficient is 1, so we don't have to do anything there for it, and divided by the concentration of H2, and we would have to cube it because of the coefficient. A reminder as well, when we see these brackets, that means concentration. And what we're usually talking about is molarity, which is our moles per liter. So that's essentially what we're talking about here. And obviously, if you had values or numbers, you could just plug it in there and get an actual number for K. This is also sometimes referred to as Kc. And C is creative for concentration. Yeah. So sometimes people will talk about the Kc value, and that's what we're talking about here. By the way, we actually have seen an equilibrium sort of value that we use, and if you remember, we saw Kw. So Kw that we saw earlier when we were talking about acids and bases, which is our H plus concentration times our OH minus concentration. 1 times 10 to the minus 14. That is an equilibrium constant, this Kw, and that's what we used earlier on in that last chapter, and it is a result of products over reactants. Now, when we do this, there are sort of a few things that we really do not include in an equilibrium expression, and there's 2 things that are really important that really don't affect equilibrium. Anything that is a solid, so anything that has sort of the S symbol next to it, and anything that's a pure liquid, like an L, is not included. So does not get included in the equilibrium expression. So if one of these guys here had a symbol of an S or an L, you would not include it in your equilibrium expression. That means there's really only 2 things that do get included, and those are things that are gases like we see here that have the G symbol, and those are things that are aqueous that has the AQ symbol. These get included. And just to show you, since these are all gases, when we think about gases, right, we oftentimes think about pressure. So you could actually write an equilibrium expression that deals with not concentration, but pressure, which is sometimes commonly what you would deal with a gas. And you could write that the K is equal to the partial pressure of NH3 squared, works the same way, still squaring it because of the coefficient. Just instead of concentration, that's the partial pressure, divided by the partial pressure of H2 cubed, again, also the 3 for the coefficient, times the partial pressure of N2, coefficient, again, 1 here, so we don't have to put anything here. This is also an equilibrium expression that is sometimes written, and since it doesn't deal with concentration, it deals with pressure. This is sometimes referred to as the Kp value. P oddly for pressure. Very creative. So there are a lot of different K values. There's KC, KP, KW, KA, KB, KSP, KF, and so forth. A whole bunch, like I said, pretty much all of Chem 1B. But really, no matter what the little symbol you see at the bottom, and again, sometimes people do include it, like KC, KP, KA, they are all basically at the heart of it equilibrium expressions. They are all products over reactants, where we only include things that are gases or things that are aqueous. And really, solids and liquids really don't interfere at all in terms of the equilibrium because, first off, a pure liquid like water, for example, will pretty much have a constant concentration no matter what happens. So, something like water, which is a pure liquid, H2O in the liquid form, pretty much doesn't change its concentration over a period of time, even though some reaction are happening. And the other thing is, if you have a solid, you can kind of visualize it like this. You know, you got like this solid thing on the bottom of the beaker. It's really not going to be able to interact in that form. The only way it would be able to interact is if it dissolved. And if it dissolved at that point, it no longer would be a solid, it would be aqueous and would be included. So you can kind of think about like solids as like rocks. If you throw a rock into like a cup or something like that, it's probably not going to do very much other than just kind of sit there. So solids really don't have an effect on equilibrium. Again, nor do liquids. Any questions on that? So as I mentioned before, the equilibrium constant is always the same value at a given temperature, regardless of how much reactants or products you start with. And again, that's really something that people have a difficult time sort of understanding. Again, it's just that idea like, hey, I dumped in more of this guy on the second time I did it than say the first time. You know, how can it all kind of come together in the same sort of proportion? And it just does. So as long as the temperature remains constant, at some point, once that forward reaction rate equals the reverse reaction rate, that ratio of products to reactants, regardless of how much you started with, will always end up being the same. Again, as I talked about, it is temperature that is the only thing that will affect the actual value of the equilibrium constant. But once you change the temperature, so for example, earlier we were talking about 25 degrees and 80 degrees Celsius. If I moved my reaction from 25 degrees Celsius to 80 degrees Celsius, and I just kept doing that reaction at 80 degrees Celsius, the equilibrium constant will once again remain constant at 80 degrees. So even if I started with different amounts at 80 degrees Celsius, it will always end up with the same ratio. Again, the difference would be between the 25 degrees Celsius K value and the 80 degrees Celsius K value. Any questions on that? All right, so take a second here and determine what the equilibrium expression should be for this reaction. Want to make sure that we use our coefficients as our exponents. So we would start with our product side here. Go here. We have the concentration of H plus, and again, we would include it because it's aqueous. We would also times it by the concentration of acetate, which is what that is. Each of these coefficients are 1, which is why we don't have to put any exponents, divided by our products, which is acetic acid, also with a coefficient of 1. So it should look something like that. So it looks like perhaps A looks like a winner there, I think. Yeah. So again, products over reactants. And again, we had no exponents in this case because all the coefficients are 1. So basically the exponent here is 1. Any questions on that particular one there? All right. So let's talk a little bit about sort of what happens if maybe you manipulate the reaction. So there are occasions where sometimes you do have to, reverse a reaction, maybe multiply a reaction, by a common number. So let's talk about what happens with that. So the question is, if you have to solve an equilibrium problem, will the equation be given to you, or will it be balanced? In a lot of equilibrium type problems, the reaction will be given to you. It probably will even be balanced. I won't say 100% of the time, so you should always make sure it's balanced, but probably in most cases, if you're sort of doing a sort of specific equilibrium sort of problem, probably going to be balanced, but always a good idea to check it just in case. They definitely will probably be given to you the actual reaction and stuff like that. Other questions? Okay, so as I mentioned before, when we do write sort of the equilibrium expression, it is specific for exactly the way the reaction is written. So what's on the reactant side, what's on the product side. And if we happen to need to sort of reverse it for a particular reason, which sometimes does occur, it does affect sort of the equilibrium value and also sort of the expression. And if we look at, say, the first one here, and we write our equilibrium expression like we did, the K would be our H2 times our CO2 divided by our H2O and our CO. Now, and that would be sort of the forward direction, but if we reverse the reaction and then this guy, for our second one, if we wrote it, the equilibrium constant expression would be H2O times CO divided by CO2 and H2. So what is really the relationship between these two? The relationship is they are the inverse of each other, right? So if you take 1 over this guy, it would flip and become this guy. So if you have a reaction and they tell you, hey, this guy has a value of 2, for example, just made up that number, but you actually want to know what the equilibrium value was for this reaction, you would take 1 over 2, which obviously is 0.5, would be your equilibrium constant for this guy. So if you have a reaction, and again, it sometimes occurs, sometimes in problems, I don't know if we'll get into a lot of this, to be honest with you, in this chapter or in this class, but definitely in 1B you will. If you're given a reaction, say you were given the top reaction and you were told, hey, the equilibrium constant is 2, and then you were given the bottom reaction and asked, what is the value of the equilibrium constant? That is how you would find it. You take 1 over the K value, and that will give you the actual value that you need for that. Any questions on that? Now, another sort of way that we sometimes manipulate sort of equilibrium reactions is perhaps we're given a reaction where we don't need 1 of everything that's there, but we really need kind of 2 of everything that's there. And so, for example, that is the difference here between the top one and the bottom one, is we multiplied everybody by 2. So a common thought would be, okay, I would just multiply, the K value by 2 because I did that. And that would not give you the actual correct answer. So just a more simpler sort of way of looking at this. Let's see here. We'll do it this one. Let's just say we had like A plus B goes to C plus D. If we wrote the K value for this guy, it would be our C times D divided by A times B. Now, let's just say I needed 2 of everybody here. So I multiplied this entire reaction by 2 and just basically put a 2 in front of our base. If I wrote the equilibrium expression for my second reaction here, it would be C squared times D squared divided by A squared and B squared. The difference between our first one and our second one is we multiplied by 2. The difference between our K values is we would actually square the K value. So because we multiplied by 2, we would take the K value and actually square it. If we multiplied by 3, we could see the effect on the original one to where we end up is we actually then just cubed it. So the difference between our original guy and where we ended up by multiply by a common number of 3 is we basically would cube it. So if you have to multiply a reaction by a common number, you then take the K to that common number. Right? So what would happen if I was the opposite sort of situation where I started with, say, this reaction? Not that. I'll try that again. Let's go here. Let's say I started with this reaction and I want to know what the K value was for this reaction. Well, if we look at the opposite way, starting at this guy and going to this guy, the difference is I just took the square root of it, basically. So if I had to divide by a common number, you would then take the K value and take the square root of it. If you divided by 3, you would take the cube root of it. And that's how you basically would adjust it. So if you multiply by a common number, you take the K value and you take it to that common number. If you divide it by a common number to find the new K value for your reaction, you would take the root of that common number. So again, if you divided by 2, you would take the square root. If you divided by 3, you would take the third root, the cube root. If you divided by 4, you take the fourth root, and so forth. So those are two very common ways to sometimes equilibrium reactions are sort of manipulated. The last sort of thing that you see in terms of equilibrium reactions is sometimes you may need to actually add two reactions together. So for example, A plus B goes to C plus D, and we'll call this K1. And maybe C plus D goes to E plus F. We'll call this K2 here. If we were to add these two reactions together, everything that is on opposite sides of the arrow that are the same will cancel. So we have a C on the left and a C on the right, so they will cancel. You kind of think of the arrows as like an equal sign. You have a D on the left and a D on the right, they will cancel. And then everybody that's on the left-hand side stays on the left-hand side. Everybody that's on the right-hand side will stay on the right-hand side. And let's say we wanted to know, what is the K value for this overall reaction? So if we look at, let's get rid of some of this here so I got something to write on real quick. Just kind of screwed out some of that. If we looked at each of these sort of K values for these reactions, if we wrote the K value for the first one, it would be K1 would be the concentration of C times concentration of D divided by concentration of A and the concentration of B. If we wrote it for our second one, it would be the concentration of E times the concentration of F divided by the concentration of C times the concentration of D. So when we add two reactions together and we want this K value here, we actually multiply these two values together. So if I multiply these two values together, the C's would cancel. And that would leave us the K3, which is our E times our F divided by our A times our B, which is what we get when we write the equilibrium expression for this. So if you have to multiply two reactions together, three reactions together to get sort of an overall reaction, and you're interested in what the K value would be for the overall reaction, you basically just multiply the K values together. So it's not add them together, which you might think you would do. You actually end up multiplying the K values. And again, just if we put numbers into here, if this guy was say 2, this guy was 3, that means that K3 would be 6 in this case, multiplying them together. Any questions on how to sort of manipulate equilibrium expressions? Okay, we will lay it up there for today. Again, a couple of reminders. We are doing acid and bases today, so that's 23, I think, in terms of the experiment. A reminder, on Monday, we do have our, I want to say final exam. We have our last exam, which is exam 4. Again, it's chapter 15 and 16. So we'll do what we normally do. We'll have a little lecture continuing on with this. We'll lay it up early, probably. We'll take it during lab. And then after that, I think one more day. So the lab that is scheduled for Monday, which is Le Chatelier's principle, will be pushed to a week from today, the last Wednesday there. So instead of checking out, which obviously we have nothing to check out, we will do Le Chatelier's principle on Wednesday. And I think we'll just forget about 16 that we never got back to. Any questions on any of that there? All right, I'll see everybody in about 15.